Motta here today to talk to us about quasi-periodic oscillation. So whenever you're ready, Sara.
Thank you very much, Tom, and thank you very much for having me here to give this presentation today. And thanks very much to all the people that came to listen to it, even if maybe some of them are actually on holidays. So I'm going to talk about quasi-periodic oscillations in X-ray binaries, even though I've not been working too much about QPOs over the last couple of years. So please forgive me if I forget to mention some crucial results that came out over the last couple of years. I did my best to check the literature, but I might have missed something. So we all know what an X-ray binary looks like. So I'm going to skip the description of these systems, which we know very well, but I will say that I only talk about low mass X-ray binaries. So those systems where the companion star is a small mass star, and this is because these systems tend to have large disks, and therefore the variability / QPO phenomenology is particularly rich. A couple of words on why we study X-ray binaries. We all know that these systems are excellent laboratories to study the extremes of physics, from the properties of the ultra-dense matter in the interior of neutron stars to the properties of matter in the presence of really strong gravitational fields, such as those we find in the vicinity of the neutron star surfaces or the event horizon of black holes, and the super energetic particle acceleration that we have at the base of the jets that are usually observed from these systems. Of course, X-ray binaries are nearby, so they're very bright and they're easy to study because they evolve very rapidly on timescales that we can easily study with our instruments. But since accretion and the jet generation processes work on the same basic principles at all masses, what we learn from X-ray binaries can be extended up to supermassive black holes powering the AGN, and therefore open a window on those systems as well. STROBE-X is specifically designed to understand X-ray binaries because of its characteristics, in particular the broadband energy coverage and the excellent spectral and temporal resolution are crucial to the understanding of these phenomena. And I hope I will show you what STROBE-X will be able to do in the future for what concerns the understanding of X-ray binaries. So X-ray binaries are really variable. We know that they vary on several different timescales. In this plot here, you can appreciate the long-term timescales in the light curves of several black hole X-ray binaries that have been observed with the RXT satellites. RXT, the Rossi X-ray Timing Explorer, will be mentioned several times in this presentation because it contributed greatly to the understanding of QPOs. So these are black hole X-ray transients. Most black hole X-ray binaries with low mass companions are transient systems, actually basically all of them, while neutron star X-ray binaries with low mass companions are most often persistent sources. But this is, from the point of view of what I'm going to say today, a relatively small difference. So this sort of variability, which goes from days to weeks to months to years, is typically described in the context of the Ardous intensity diagram. I'm sure you've seen this diagram many, many times over the years. This is conceptually similar to the Earth-Russell diagram that is used in stellar evolution, with the property that one single source that becomes active enters the outburst phase, or just active in the case of neutron stars, for example, traces a typical Q-shaped pattern that looks like this and is traveled anti-clockwise. So these are all the points from the sources that you've seen in the previous slide, but every single source traces a loop that looks like that. Sources start their outbursts over here in quiescence, and they rise up in luminosity, and they travel this loop in that direction. In the case of neutron stars, sources live in this plane most basically all the time. In the case of black holes, we have quiescence and we have outbursts. This diagram is divided in different accretion states. There are three main states: the hard state here on the right, the soft state on the far left, and the intermediate states, which are actually two states really close together in hardness. The reason why sources move into this diagram is typically explained in terms of the truncated disk model. There are other options, but this particular model, I believe, is the one that explains most of the properties that we observe from X-ray binaries. So I'm going to focus on this one. The idea is that the accretion flow is formed by a geometrically thin, optically thick accretion disk, which is truncated at the certain radius, which is the truncation radius, the inner truncation radius. And from this radius inwards, down to the innermost stable circular orbit, it is replaced by a geometrically thick, optically thin accretion disk. The idea is that in the hard state, the truncation radius is large, and it decreases during the intermediate states and reaches a minimum close or in the soft state. When sources go back to the hard state after spending some time in the soft state, the truncation radius decreases again up to a point where the source goes back to quiescence. So the thick disk, the blue stuff over here, is what generates the hard non-thermal photons that we see in the spectra from X-ray binaries, and the most variable photons as well. While the thin disk, the red stuff over there, is responsible for the spectral components from the soft thermal black body-like photons that we see in the spectra. Of course, in the hard states, we have the spectra dominated by the hard photons. The spectra look like that, and we have the most variability because those photons are the most variable. In the soft state, we have spectra dominated by the disk emission. They look like that, and the variability is really low. In the intermediate states, as you can imagine, we have some intermediate situation, both for what concerns the spectral properties of X-ray binaries and their variability, the overall variability. The X-ray binaries are characterized by variability. We said that already quite a few times, but the variability that characterizes them the most is the fast time variability. And I mean by that, all that happens above 1 Hertz, more or less, or above a few millihertz, up to several hundreds or even 1,000 Hertz. We have all sorts of modulations in the light curves from these systems, X-ray light curves from these systems. We have coherent pulsations, for example, from accreting millisecond X-ray pulsars. These are just pulses, so very deltas in power density spectra. We have really broad components in the power density spectra, such as ones that you see here that cover very large frequency range and carry a lot of variability, but not coherent, not a coherent type. And then we have everything that is in between, which includes quasi-periodic oscillations. I'm going to say quasi because quasi is latent, so I'm not going to say quasi. Apologies to all the Americans and British speakers that are listening to me. What are quasi-periodic oscillations, or QPOs? These are quasi-periodic modulations in the signal from a source, from an astrophysical source, in this case X-ray binaries. So the modulations that we observe are mostly detected in the X-rays from these sources, but sometimes we see QPOs also in infrared and in the optical, but most often we observe them in the X-rays. QPOs have been observed in essentially all accreting systems, from CVs, of course, X-ray binaries, CLXs, and even up to AGN. Of course, they have different frequencies in the various systems, and they have different origins as well. Since these signals tend to be really fast, we study them in the Fourier domain. So we use power density spectra to study them. And in power density spectra, they typically come associated with broadband components that we call noise, which are specific to the type of QPO you're looking at. So whenever you see a QPO, the noise will help you classify this QPO because the noise is strictly correlated to the QPO that you're looking at. Over the years, we detected many QPOs in many different systems, and several types and classes have been defined. But before I give you all the, an observational overview of what we know of QPOs, let's stop a moment and let's ask why we care about QPOs. So from a very basic point of view, they are really useful in the sense that QPOs are strictly connected with the accretion states that a source is crossing at a given time. So there are different QPOs in different states. So anytime you observe a source, the type of QPO that you're observing is giving you information about the state that the source is crossing, which means that you will know what's going on in other bands, even if you do not observe the source in other bands. For example, radio is a typical band that you want to know what's actually showing, as well as you will probably also get information about the rough information about the geometry of the accretion plot at the specific time where you see a QPO, and what you can expect in a short time if you want to follow the evolution of the source in time. From a more sort of hardcore physics point of view, QPOs, remember, are produced really close to the compact objects that power X-ray binaries. They come really close to those regions where GR reigns. So QPOs speak GR. They carry a lot of information about what happens to matter in the presence of really strong gravitational fields. Therefore, they are really useful in the sense that they will teach us, if we manage to understand them properly, information about the behavior of matter in that region, and also the specific properties of the compact objects that they are producing them. So it is really important to understand them fully. Like QPOs, we said, come in different flavors. There are two big groups of QPOs. The first one is the low frequency QPOs. Of course, you have also the high frequency QPOs. I'll start from the low frequency QPOs. I'm going to focus on black hole QPOs because it's a bit simpler in terms of classification, but what I'm going to say now basically applies almost exactly also to neutron stars. Their QPOs are called with different names, but the essential information is the same. So I'm not going to dwell too much on names and details about them, of classifications more than names. So, QPOs were discovered in the 80s, first in neutron stars and then in black holes by the ExoSat satellite and by the Ariane 6 rockets. The first evidences for the existence of different types of QPOs come from observations done with the Ginga satellite. And after then, we observed QPOs in essentially all binaries we observed. And we have hundreds of detections only in the RxD archive. Of course, other instruments contributed to the understanding of QPOs, but RxD, I believe, was responsible for a really huge jump forward in the understanding of this phenomena. And in fact, as I will say in a few slides, RxD allowed the discovery of high frequency QPOs. So that was its contribution was really, really important to the field. There are different types of QPOs. As I said, I will start from the type A QPO. This is really the least common of all among QPOs in the RxD archive, which is the biggest archive for the study of QPOs that we have. The NICER archive is getting close, but it's not there yet. The RxD archive includes order 10 detections of type A QPOs, so there are really not many. These type of QPOs appear in the soft states just after the transition from the soft intermediate state, close in time, generally speaking, to the appearance of type B QPOs that are very transient features. Type A QPOs look like this. In the plots, you see an example from GX339-4. They appear at about 7 Earths. They normally do not appear at particularly significant lower or higher frequencies, and they come associated with this power law red noise in power density spectra. So the peaks are broad and faint. The intrinsic amplitude seems to be quite low. And that's it. We basically don't know anything else about type A QPOs, really have no clue about what's their origin. It has been suggested that they might be related to disk instabilities, mostly because sometimes they look a bit like type B QPOs, but that's it. We don't really have enough information to say much more about the origin of this type of QPO. Type B QPOs are quite common in X-ray binaries, black hole X-ray binaries, but of course also in neutron star X-ray binaries, where they're called MBOs. These QPOs are observed in the soft intermediate state over here in the Arden's intensity diagram. And according to the Belloni and Oman classification, this state, soft intermediate state, is defined based on the presence of these QPOs. So you don't have a soft intermediate state if you don't have a type B QPO. Type B QPOs look like this. They generally appear as a really strong peak with a very clear centroid frequency, typically accompanied by harmonics, what we call subharmonic, probably in an improper way, and a second harmonic, which is generally not as strong as the first harmonic. And the frequency where you see type B QPOs is the frequency range is centered about 6 Hz. Sometimes you see them also at quite lower frequencies. I'm thinking about the case of, again, GX39-4, where type B QPOs are also observed at 1-2 Hz when the source goes back to the hard state after spending some time in the soft state. About the origin of the type B QPOs, what we know for certain is that type B QPOs appear in a phase of the evolution of a source during its outburst where relativistic jets are observed. So these QPOs have been associated quite often to the generation of relativistic jets. So it has been speculated that they are related to whatever is generating the jet as well, even though we do not have a model that explains how this happens. This is still definitely very much under debate. There are, of course, suggestions, and a few models suggest that type B QPOs might be due to these instabilities that are triggered by the launch of a jet in one way or another. But again, this is still to be clarified. Finally, type C QPOs. This is where the story changes quite a lot. Type C QPOs are the most common type of QPO we have. And differently from the type A and type B QPOs, they vary a lot in frequency. They are observed in a quite large frequency range from a few tens of millihertz up to 30, 40 hertz. And they are observed basically in every accretion state. Of course, we observe them more often in the low, in the hard state and in the intermediate, hard intermediate state, but they also are observed in the soft state and in this called anomalous or ultraluminous state, which is a state, an accretion state that is not very common. Only a few sources go there, and this is essentially a very high luminosity state that looks a lot like the soft intermediate state, but just with much higher luminosities and probably accretion rates. Type C QPOs look like that. They are really strong peaks, normally accompanied by several harmonics. You have a train of harmonics in some cases, 3, 4, 5 harmonics in the power density spectrum, and they come associated with this really strong noise component, which is called sometimes flat top noise because of the characteristics of being flat and cutting at some frequency, which is typically around 1 Hz. This is what you should think of when you think QPO. This is the look that type C QPOs have in the harder states. When they are observed in the soft states, they look a bit more crappy, a bit more lower amplitude. The noise also is a bit less strong, if you want, but they retain their most important characteristics. Maybe because type C QPOs are so common, there are several models that attempted to describe what's the nature of these QPOs, and there are and all the models that we have, or the majority of the models we have, can be divided into different families. The first family is a family of models that assume that the modulation, the QPO modulation, comes from something that is actually oscillating in the system. So, for example, you have the oscillation of a boundary layer of a corona, or some other portion of the base of the jet, or some other portion of the accretion flow, or similarly, you have an instability that triggers some oscillation of something in the accretion flow. The other family involves geometrical effects. So the modulation is not intrinsic to the accretion flow, but is imprinted by some geometrical effect. This is a very nice plot that Adam gave to me many years ago now, which sort of shows what I mean in the case of relativistic precession of matter around the black hole. The relativistic precession of matter does imprint a geometrically induced modulation to the emission of X-ray binaries. I'm not going to give any more details about these models for now. Adam and I wrote a review a couple of years ago. You can go there and look at the list of the models that we collected. If you want to learn more about all the models that have been proposed over the many years after the discovery of QPOs. Now I'm going to give you a description of the main properties of QPOs that might be interesting or important when we want to try and understand this phenomenon. So one of the most important properties of QPOs is that they have hard spectrum. So if you manage to extract a QPO spectrum using Fourier result spectroscopy, like in this case, like in this very nice paper by Małgorzata Sobolewska, you will see that the spectrum of the QPO really looks like the Comptonized emission that we see in the spectra. The same sort of information you can sort of obtain measuring the RMS from QPOs, all the three types of QPOs, as a function of energy. You will see that the RMS spectra, like in this paper by Giorgio Casella, the RMS spectra peak at around 20 keV, and there is little to no variability below a few keV. Because, as I said, the spectrum of QPOs peaks at the high energies, and there is basically no variability where the disk dominates. STROBE-X will be perfect to study QPOs and will have the perfect response to these sort of studies. Of course, the labs will be sensitive to the high energies up to 30 keV, so it will collect all the variable photons that will come from the X-ray binaries that are going to be observed. But the XRCA also will have a very important role in this. The XRCA, with the very large collective area that will feature, will be able to collect a lot of photons, including the few photons that still belong to QPOs that basically escape to the softer energy. So this is really unexplored fields, and it will be exciting to see what we are gonna be able to find once this count statistics increases by a factor of 10 or more with respect to the instruments we've been using so far. Again, related to the connection of QPOs with the hard emission from X-ray binaries, we know that the frequency of QPOs correlates in different ways with the hard flux. In particular, the type E QPOs correlate with the hard flux, so the flux from the non-disk emission. In a nice power law-like way. This is a correlation that exists in the data from GX39-4 again, but this has been observed in other sources as well. Type C QPOs behave in a totally different way. You see that sometimes the flux correlates with the frequencies, and sometimes the frequency does not correlate, anti-correlates with the flux. And these two totally different behaviors suggests something that was not completely obvious a few years ago, which is that type E and type C QPOs are different things. There were suggestions maybe 10 years ago or even later, or even earlier, I don't really know, that type E and type C QPOs might be essentially the result of the same phenomenon, just evolving a bit during the outburst of a source. So something that would change a bit phase over time, but essentially were the two phases of the same thing. In reality, this cannot be true because we do observe type E and type C QPOs together at the same time. And this confirms and allows to establish that these two QPOs, or these two phenomena come from, have different origins that might be connected. That's not to be excluded, but they are different things. This sort of situation, a type B and a type C QPO together, happens in different sources. This perhaps is the best example because of the super high statistics. This is GRO J1655-40, and this power density spectrum comes from an observation taken at the very top of the ultraluminous states. You see that counts per second PPCU was huge, so the statistics was ridiculous. But the same sort of thing can be seen in other sources. These are the sources where this situation occurs more than once. There are other sources that show something similar. In all cases, however, it looks like type B and type C QPOs are seen together when the accretion rate and the luminosity are really high. So this might tell us something about why they do appear together when normally they do not. And in fact, what we see often enough in the data from X-ray binaries is switches between different types of QPOs. Here on the left, you have again GX39-4 and RxC data, where you see a type B QPO that leaves place a type A QPO, and the transition takes just a second or even less. This on the right instead is the case for MAXI J1820, and the data this time comes from NICER. You see a nice type C QPO evolving in frequency quite a bit, and then switching off and leaving place to a type B QPO. Now, we've just said that type C QPOs and type B QPOs can be observed simultaneously, so there is no doubt that those things are not the same thing, just changing a bit. This is not not so clear for the case of type B and type A QPOs, because type A QPOs, okay, they are very rare, but they've never been observed together with another type of QPO. They're only seen alone. So it's not completely clear if they really are something separate or not. And in fact, if we move to neutron stars and we assume that the connection between QPOs that I mentioned earlier and that I will describe a bit better later on is correct, the equivalent, the QPO that is the equivalent of the type A QPO and the QPO that is the equivalent of the type B QPO evolve one into the other. This is the case of SCOPUS-X1, but this is seen in other Z sources as well. So it's not so clear. We need more data to say more about this. There is a concrete possibility that type A QPOs are in fact some sort of really crappy type B QPO or really crappy type C QPO, for what we know. We will have to collect more data to be sure about what's going on there. Inclination, we all know it's really important when studying X-ray binaries. We know that a lot of things change depending on inclination, as well in X-ray binaries and in AGN. We've seen this picture of an AGN many times, I'm sure. And there are, of course, a lot of things that change in X-ray binaries as well, depending on inclination. We know, for example, that only high inclination sources show strong winds, and this is because the winds that are produced in the soft radio-free states are launched in an equatorial direction, so at very low angles with respect to the plane of the disk. Therefore, we will see winds only in sources where our line of sight crosses the winds, and so much so that the effects of absorption will show up in our fine spectroscopy spectra, energy spectra, essentially. In a slightly, well, in a similar way, maybe, high inclination sources show disks that look hotter than low inclination sources, and this has to do with the fact that the disk being inclined implies that there will be projection effects and relativistic effects that will essentially boost the emission from the disk in the direction of the observer, making the disks look hotter in high inclination sources. This goes without saying. QPOs as well, of course, care a lot about inclination, and there is a clear correlation between the orbital inclination of a source and the amplitude of QPOs. Type C QPOs look stronger in high inclination sources, so those sources where that are observed essentially edge-on, and they look quite significantly fainter in sources that are observed face-on, so at low inclination with respect to the line of sight. The opposite is true for type B QPOs, that will look stronger for face-on sources, and they will look fainter in edge-on sources. Something similar goes on for the noise as well. So the noise, the broadband noise, this component here, that comes with type C QPOs looks stronger for low inclination sources. So the opposite that we see for the QPO. So the type C QPO is stronger high inclination sources. The noise that comes with the type C QPO is stronger for low inclination sources. Well, we cannot tell much about the noise connected to type B QPOs. It looks inclination independent, but this might have to do with the relatively limited number of type B QPOs that we have. So the variability of X-ray binaries, the quasi-periodic variability, and the overall variability does know about inclination, and this is also a result that was obtained by Lucy Hale in 2014 using the power colors. You can go check her paper. This is a very nice piece of work that describes an alternative way to use power density spectra to trace the evolution of a source over an outburst. I really recommend this paper to anyone is interested. And again, about QPOs and inclination, the lags of the QPOs also know about inclination. So in this case, I'm only talking about type C QPOs because type B QPOs, the statistics connected with type B QPOs was not enough to say much. in this context, but in this very nice paper by Jacob van den Eynen, it was shown that type C QPOs, the lags associated with type C QPOs are hard in low inclination sources and are soft in high inclination sources. So first of all, a QPO lag, by QPO lag, I mean the integrated lag measured around the QPO centroid frequency in a very narrow frequency range. And by hard lags, I mean that the hard emission lags the soft emission, and opposite, of course, for the soft lags. So we know this is going on. We don't really know what's going on with type B QPOs because we had a limited number of detections and the signal to noise was not good enough. But STROBE-X will confirm these results and will tell us more about type B QPOs because the signal to noise will be increasing by a factor of a lot. And I'm sure that this sort of lacking knowledge will be definitely filled. So I've mentioned neutron stars a couple of times already, and the comparison between neutron stars and black holes is quite natural because we know that these systems, broadly speaking, show very similar characteristics. In particular, Theo Munoz-Darias in 2014 published a very nice paper where he showed that the hysteresis behavior that is typical of black holes is also seen in neutron stars quite clearly, actually, and the same states and transitions are observed. This has been observed, of course, in many sources in the past, previously before Theo arrived with this paper, but only in individual sources. This paper systematically probed this sort of property in a large number of neutron stars. And the fact that we can approach neutron stars and black holes in the same way, of course, allows us to study the variability of these systems in a much larger number of systems. Neutron stars are more than black holes, really. There are more neutron stars than black holes in the galaxy. The good thing is that also QPOs are very similar in neutron stars if compared with black holes. This is the connection, the association that has been made between the QPOs in black holes, this one on the left, and the QPOs in neutron stars. So don't mind the names too much. They are just defined based on historical reasons that don't really matter now. But there is this association. The only question mark is, again, as I said earlier, the type A QPOs. We don't have that many type A QPOs, as I said, so the connection with FBOs is not really clear. But however, if you just forget for a moment about that and you check the properties of QPOs in black holes and neutron stars, you will see that there are really no big differences. What QPOs really care about is the mass of the object that is inside the system. They don't care about surface, they don't care about magnetic fields, they don't care about anything, or obviously care about anything that is not the mass. If you look at these two plots, you will see that in black holes, QPOs span a relatively narrow frequency range from these are, well, all the type of QPOs, type C QPOs are there, then here you have type A's and type B's. They span a relatively narrow frequency range from about 0.1 Hertz or 20 Hertz, so 30 Hertz maybe, while neutron stars span a much larger frequency range. And this, of course, has to do with the fact that neutron stars are at least 2 times smaller, lighter than black holes. If you look at them, if you look at QPOs in the polar density spectra, you will see that neutron star QPOs are a bit more happy maybe, but they really are quite similar to what we see in black holes. And in fact, here I picked the best looking QPOs for black holes, so most of the time they look basically identical. So there is no big difference there, just the cosmetics if you want. So first sum up before I move on to high frequency QPOs. I told you that low frequency QPOs have a hard spectrum, and this is actually true for high frequency QPOs as well. And they correlate in different ways with respect to the hard flux from the X-ray binary that produces them. They do care a lot about inclination, their lags do too, and the overall variability from a binary knows about inclination. So this is quite important. There are definitely 2 separate classes of QPOs, type B and type C QPOs. Maybe, well, there is a third class. We've classified QPOs in 3 classes, but it's not completely obvious if the type A QPOs are a totally separate class with different physics, or if they are connected with the type Bs or the type Cs in some ways. For what concerns the origin of QPOs or low frequency QPOs, Type C QPOs are most likely the result of a geometrical effect. For example, the relativistic precession of matter around a black hole or a neutron star can explain the properties of type C QPOs quite well, actually. We know that the type B QPOs are most likely connected with the mechanism that is at the base of the launching of the radio jets that we see in X-ray binaries in transition, but we still do not have a model to explain them fully. And we don't really know about type A QPOs, really need more data. High frequency QPOs are the second big group of QPOs that we have. They have been discovered by RXTE in the 90s, first in GRX 1915 + 105. I'm sure you all know about this source, where, however, the high frequency QPOs are not high frequency at all, if we want to be precise, because the high frequency QPOs in 1915 are seen at about 70 Hz. High frequency QPOs, differently from low frequency QPOs, are quite rare, and they're difficult to detect because the intrinsic amplitude is not very high. And particularly rare is the detection of high frequency QPOs in pairs. So why do we expect them to appear in pairs? This is because in neutron stars, high frequency QPOs, which are called killers QPOs there, are much more common, and they do appear in pairs, and they are called twin killers QPOs. And there the amplitude of these QPOs is much higher, and it's quite a lot easier to detect and study them. A systematic study of focused on high frequency QPOs performed in 2012 found only 42 detections of high frequency QPOs in only 7 sources, and these 42 detections became 11 from 2 different sources only when the number of trials were considered to determine like the significance of the detection of the signal. As far as I know, there is only 1 detection of a high frequency QPO in NICER data. I'm not even sure if this has been confirmed. If somebody knows about this, please, I would love to know as well. And I'm not aware of any other high frequency QPO from other instruments, I think. So again, these are faint and rare. And for what we can tell from the 42 or even 11 detections we have from RXTE, they tend to appear at high luminosity. But this could be an observational bias because, of course, as you can imagine, the high luminosities, you have a lot of photons coming to your instrument, so the count statistics is really good. So this may be the reason why we do have most of our high frequency QPOs at high luminosities. The discovery of high frequency QPOs stirred a lot of interest because the frequencies of these signals are close to the Keplerian values that you expect from matter orbiting a black hole or a neutron star near the innermost stable circular orbit. And this is the reason why there are so many models that try to explain high frequency QPOs. Most of them have to do with the predictions of GR and the characteristic frequencies of matter orbiting a compact object. Most of these models, if not all of these models, are based on mix of the characteristic frequencies of matter orbiting a black hole. This here is a small list of models that have been proposed shortly after the discovery of high frequency QPOs. It's definitely not exhaustive, but it could be a first step if you're interested in learning more about high frequency QPOs. The one model that I know best is the relativistic precession model. I used this model a few years back. And I tested the goodness of this model, which was originally proposed by Luigi Stella and Mario Vietri in 1998. The basic idea is that QPOs around a black hole or a neutron star can be associated with the orbital motion of matter around the compact object, the periastin precession of the non-circular orbits around the compact object, and the length-steering precession of the same orbits, so the nodal precession of the orbits in this case. the three QPOs that are associated with these three motions are the upper high frequency QPO, so the one of the pairs that is observed at higher frequencies, the lower high frequency QPO that is observed at slightly lower frequencies, and the type C QPO, which is observed as we've seen earlier around 10-20 Hertz. If you look at these equations here, which describe the which show like the analytical form of these equations according to GR, calculated in Kerr metric for planar orbits, you will see that they depend on three unknown parameters. One is the dimension of spin, the other is the mass of the compact object, and the third one is the radius at which the modulation arises, so the radius of the orbit you're considering. Now, if you can associate these three frequencies to a QPO, you will be able to plug a number in these three positions, and these three equations become a system of three equations in three unknown parameters, which can be solved exactly. So this is what we've done in the case of GROJ 1655-40, which did show a type C QPO and two high frequency QPOs. This was a discovery by Strobe-X in 2001, I think, if I'm not mistaken. And using these equations, essentially, we managed to solve the system, therefore obtaining a mass and the spin, with one big caveat, which is that the radius, this unknown here, is the same for the three QPOs. So this is the reason why we want the three QPOs together, because it's a bit less tasking to assume that the three QPOs arise from the same portion of the accretion flow, which is characterized by a special radius. So this is what we got for 1655. The mass was this one, and this was the spin. The most important thing to remember is that, or to mention, is that the mass is fully consistent with the mass from spectrophotometric optical observations of the same system, which return a mass that is only slightly larger than that value there. A similar method I used to obtain the spin from the black hole in XTJ 1550. In this case, we only had two QPOs, a type C and a lower high frequency QPO. So in order to be able to solve the system, we used the mass also from optical observations, and this was the spin that we got. For many years, this was it, right? This happened in 2014, and we didn't have any other source that showed the QPOs that were relevant for the relativistic precession model, so we couldn't really do much more than this. We did try this method on neutron stars. I'll show you something in a moment. But recently, I found a new QPO triplet that could be used with the relativistic precession model in the RXTE data from XTE J1859. The XTE archive is still a goldmine. I really love RXTE. Anyway, so these were the three QPOs that I used, and these are the estimates of the mass and spin only based on timing. Again, the mass is fully consistent. This time is even better. Actually, the match is even better with the mass from the optical observations, even though the uncertainty there is a bit larger. The results from the X-ray timing are reported in a paper that has been accepted, but is still on hold because we're waiting for the accompanying paper reporting the optical mass. So you will see these papers in a few days, hopefully, on the archive if you're interested on the details. As I said, we tried this method on neutron stars initially using the Kerr metric, which of course is not completely appropriate to describe neutron stars because there's a surface there. But we did get something relatively sensible, even though the mass that we got was a bit on the high side. But we did also try this method using a metric that was a bit more appropriate for neutron stars, and we got a mass that was slightly smaller for the same source that we use here for U1608, and two more sources, and the results are reported in Maselli et al. 2020 if you want to take a look. Second summary before I move to my conclusions. High frequency QPOs in black holes are very rare, as we've said, but they're really common in neutron stars. But the fact that they are rare might not be intrinsic. Maybe it's just that we do not look very well because our instruments do not feature the properties to accumulate the right count statistics. So STROBE-X definitely will help in this. As I said, it looks that now they appear at high luminosities, but this might be just an observational bias. The frequencies that proper of high frequency QPOs are close to the Keplerian values, and there are many models that explain these type of phenomena, but only a few of them have been tested thoroughly. And this is not good. We really need to test all the models, not just the few ones that some people like. For example, like relativistic recession model, we need to test them all because this is the only way to actually progress in the understanding of these things. So I hope I convince you that we can do amazing things with QPOs, and STROBE-X will help massively in the understanding and in the knowledge of QPOs, because it is the perfect observatory to study these phenomena because of these. Of course, it's excellent time resolution, which is crucial for precise frequency measurements. But in my opinion, most importantly, because of the response, the sensitivity to the high energies, and the broadband response, as well as the large collecting area, will be extremely important to improve all we've done so far in terms of testing the models of QPOs, or actually detecting new QPOs, and will certainly allow us to get more information and new, really exciting results in these fields. I'm going to stop here, and I'm happy to take questions if